Well, hi there, boys and girls. Today we're going to talk about optimization, and that means we're going to try and find the largest or the smallest thing possible given a problem situation. And before we do this, we're going to have to know about something called the second derivative test. And this is a way of verifying whether we have a relative max or a relative min at a critical point. So let's just talk about what the second derivative test says. If f double prime of x is greater than 0 at a critical point, what does f double prime greater than 0 mean? If the second derivative is positive, that means we are dealing with a concave up graph. And this should make sense that it would be a relative minimum, because if we have a flat spot on a graph that's concave up, then that's going to be a minimum. The second thing says if f double prime is less than 0, which would mean concave down at a critical point, then that's a relative maximum. And that should make sense as well. If you are at a critical point and your graph is concave down there, you have created a relative maximum. If for some reason the second derivative works out to be 0, then you need to go back to the first derivative test, that thing right there at your critical point, and check and see if f prime goes from positive to negative or negative to positive. So let's just jump right into a question here. What is the area of the largest rectangle that can fit in one arch of cosine x? Largest. I am trying to optimize or make something as large as possible. That should be an E there, optimize. Let's go take a look at this picture. I've got one arch of cosine. I just decided to pick the one that's symmetric across the y-axis, and I'm going to pick some point in here, and I'm going to make a rectangle through there. And I want to figure out how big of a rectangle can I put in there. So let's go ahead and there's our picture. Let's label these points. This point right here would be x, comma, cosine x. And this point over here would be negative x, comma, cosine of negative x. And let's talk about the area of this rectangle. Let's go ahead and draw this rectangle. Get a little rectangle shape here. So I'll blow it up over here. And let's label it. What would be the height of our rectangle? Well, I can use this height over here. And by the way, it is a rule that cosine of negative x equals cosine of x, because it is an even function symmetric across the y-axis. So the height of my rectangle is cosine x. Now what is my width? My width is I've got negative x to the left and positive x to the right. So how far is that all the way across here? Well, that would be a length of 2 x's. So my area in terms of x is 2x cosine x. What we want to do is we want to maximize that function. And how do we maximize something? Where can a maximum actually occur? Maximums can occur where f prime of x equals 0, and on top of that we need it to be going from positive to negative. But we're also going to verify this with the second derivative test. So we're going to get our calculator out and we're going to actually find the derivative of 2x cosine x. We'll get to the home screen. And so I'm going to calculate the derivative of my area equation. So I want the derivative of 2x, and by the way, you have to do multiply here. You can't just type in 2x cosine x, because some of the calculators won't do what's called implied multiplication. So I want the derivative of 2x cosine x with respect to x. I just want to see what a prime is. I'm going to hit enter here. So a prime equals, I lost my calculator, 2 cosine x minus 2x sine x. So that is my derivative, and I need to find a place where that crosses the x-axis from positive to negative. So what we're going to do is I'm going to copy that and paste it and go graph it. So we're going to copy it, and then I'll go to y equals and I'll paste that in. Okay, so let's take a look at this picture. I need to know where that is crossing the x-axis from positive to negative, and it looks like it happens right there. This would be a minimum, this one is going to be a maximum. this is A prime going from above to below. So I'm going to hit F5, and I want to find a 0, where A prime equals 0, lower bound 0, upper bound, I think that's 1, and then enter. And it found the 0 to be 0.860334. When x is 0.860334, that looks like to be a maximum. X equals 0.860334. Now, the question did not ask me what x value created a maximum. It says what is the area of the largest rectangle that can be put inside of cosine. So what I have to do is I have to find the area by plugging in 0.860334. So I'm going to plug that into my area equation, which is 2x cosine x. So we're going to go to the home screen, and we're going to do 2 times 0.860334 times the cosine of 0.860334. And I'm going to hit enter, and it looks like that area is 1.12219. So that is the maximum area. Now I want to show you by using the second derivative test whether or not this is this x value is a max or a min. So let's go back and look at that. So we're going to go to the home screen. Oh, no, I know that I'm recording. I'll go to the home screen here, and I'm going to find the second derivative of our original function. So I'm going to come back and have that be comma 2, and I'm going to close parentheses, and I'm going to evaluate this at x equals 0.860334. Now this is just going to prove whether our critical point is a max or a min. Remember, for a maximum, we need this value to be negative. So let's just see if that's the case. And we can. We see that A double prime is negative at that critical point. That proves that we have found where a maximum occurs. A double prime is less than 0 at 0.860334. So this proves that we have found a maximum. And that maximum area is right here. All right, let's go do another question here. I've got a cylinder can, and I want it to hold 20 pi meters cubed. So that means that the volume is 20 pi meters cubed. And by the way, that formula for the volume of a cylinder is pi r squared h. It says the material for the top and bottom costs $10 per square meters, and the material for the side costs $8 per square meters. I guess the material for the top and bottom needs to be stronger, so it would be more expensive. I don't know. Find the radius and the height of the most economical can. Well, the most economical can is going to be the cheapest can. And that means that we want to minimize cost. If you ever happen to make a business, you actually might answer questions like this. You want to minimize cost, maximize profit, things like that. So let's come up with a cost equation. So I'm dealing with the surface area here. In the surface area of the cylinder, I have 2 pi r squareds. That's the 2 circles on the top and bottom. And then plus 2 pi r h. That is your lateral surface area for a cylinder. So my cost equation is, it's $10 for the material on the top and bottom, plus it's $8 for the material around the sides. That's called the lateral surface area. Now, we do not, this is a pretty intense equation because I've got 2 variables here. I've got radius and height, and you do not want that. You want to put this in in terms of one variable. So I've got this original equation up here that I can maybe substitute for. So since 20 pi equals pi r squared h, then I have a relationship between r and h. So I can substitute for one of these over here. So I could substitute 20 over h for that r squared, but then I'd have to substitute for this r as well. So it looks like it'd be better if I solved this for h. And I can just take that right there, 20 over r squared, and plug it in for the h. So my cost equation is going to be just a function of the radius. So I've got 20 pi r squared plus 16 pi r, and that h is 20 over r squared. So let's simplify that just a little bit more. The cost as a function of radius is 20 pi r squared plus 16 times 20 is 320 pi over r. Well, I've got r to the first on top and r squared on the bottom, so that's over r. So there is my cost equation. And now what I want to do is I want to find the derivative, and I want to set it equal to 0. And I'm going to do that on the calculator. So from the home screen, I'm going to take the derivative of 20 pi, I'll use x here, x squared plus 320 pi divided by x. I want that derivative, and I want it comma x, close parentheses, and we're going to hit enter. So there's our derivative. So I'm going to go up there and grab that, copy and paste it, and plug it into the y1. Yes, I'm just curious why I've got those decimals there, but maybe I've got it on. Let me check my mode here just real quick. Got it on approximate. I think I want to change that back to auto. Let's do that again. So there's the derivative. Yeah, I like this version much better. I don't like the decimals up there. Okay, so let's go up here and copy this. Go to y equals and paste it. Well, it doesn't look like I copied it very well, so let's try that again. Copy. I think you're right, Kelsey. I wish that thing would flash anytime it actually copied it. Maybe I didn't hit enter here. I don't know. Boy, I am struggling. Every day I'm struggling. I want to clear that, and we're going to... Oh, I think I've hit home twice. I am wasting your time. I apologize about that. Be patient with me, please, here. And then paste. Enter. Finally, Mr. G was successful. My goodness. Now, I probably don't have a very good window here, so let's change my window to look from... I'll just go from -2 out to 10. And then graph. Don't have a very good window here, but it looks like it's going to happen somewhere between 1 and 2. I'd like to look a little further up and down, see a better picture. -2 y minimum, y maximum of 10. Go back and graph it. Okay, well that didn't change things at all, but still, you can tell it's going from positive to negative. Well, maybe you can't, but we'll check the second derivative to make sure. So I want to calculate a 0 here. Go to 0, and it looks like it happens somewhere between 1 and 2. And that happens, well, exactly at 2. Let me try that again, make sure. I'll go from 1 to 3. A 0 from 1 to 3. Yep, that happens at 2. So C prime equals 0 when R equals 2. So if the radius is 2, well, what's the height? Well, the height is 20 divided by r squared. So the h is 20 divided by 4, which is 5. So there are, and that's the question, the radius and the height of the most economical can. I want to go back and just make sure that I have found a maximum. So from the home screen, I'm going to take the second derivative of this function, and I'm going to plug in 2 and see if I'm going to get a negative value. Remember, second derivative test says if the second derivative is negative at a critical point, then we have proven a maximum. So I'm going to evaluate this at x equals 2. I'm going to hit enter, and it's positive. Well, that's because I'm supposed to be making a minimum, aren't I? I'm minimizing cost. Oh, well, sorry. Anyway, we were minimizing cost, and I was confused there because that's a positive answer. So we found that our derivative, second derivative, was positive. That means that we have made a minimum from the second derivative test. So I'm going to come back here and write this. So I'm going to say that C double prime of 2 was less, I'm sorry, boy goodness, was greater than 0. And that means that we have created a minimum by the second derivative test. So I'm going to go ahead and stop because I can't stop speaking for some reason. And I will see you guys on Wednesday.